sharp.
Good luck.
All right, so it is 1 p.m. Central European time. So I think it's time to start this webinar. Welcome, and first of all, happy Global Accessibility Awareness Day, the 10th anniversary of the Global Accessibility Awareness Day. I'm very happy to see that so many of you have joined us today for this special event that we've entitled Emerging Tech and Accessibility. My name is Emil Geroth, and I'm a researcher at Funka. That means, among other things, that I do research studies on various topics related to accessibility and tech. Most recently, I did a study on how extended reality and other emerging technologies might benefit persons with disabilities. And while conducting that study, I came across loads of interesting solutions from all over the world. It's really fascinating to see. And that includes the work of the 3 practitioners who we've invited to join us here today. And I thought I'd just introduce them very quickly. So with us today, we have Valentin Weilengong, who's been part of a team that developed an adaptive input interface for persons with mobility impairments. We're also joined by Chiara Valsolga, whose PhD research revolves around the use of extended reality as a rehabilitation tool for persons with hearing loss. And finally, we're also joined by Paul Denoy, whose work includes using augmented reality solutions to help persons with vision loss with navigation. So welcome to all of you, and I'm really glad that you were able to join us today to talk about your work. And in just a moment, you'll each get an opportunity to tell us more about your work and your research and the solutions that you've developed and how it contributes to more accessible societies. After your presentation, we'll open up the floor to questions. And if you think of a question during the presentations, then please put them into the Q&A section, which you can find by looking at the menu at the bottom of the screen. There's a button that says Q&A and has 2 speech bubbles. So if you put your question in there, we'll see it, and we'll try to get to as many questions as possible, but we'll save all the questions for the end. And you might also notice that we're providing captions and a live transcript for this event, which you can activate by clicking the button that says live transcript and then show subtitle. And I can see there's a question about whether or not this event will be recorded. And yes, it will be. We will record this event. I think the recording has already started. And then we'll put the recording up on our YouTube channel after the event so that you can go back and see it if there was anything that you missed. With that housekeeping out of the way, I'd like to hand over to Valentin, who will be the first person to present his work to us. So Valentin, please, the floor is yours.
Hi guys, I'm Valentin. I'm just gonna share my screen first. Here we go. So hi, I'm Valentin. I'm currently a master student at the University College of Art and Imperial College London. And I've come from a background of design and engineering and business as well. So I position myself at the intersection between design, business, and technology. And before my study, I also used to work with several big organizations, from VR, AR to AI to drones, robotics, and so on. And today, I really want to talk about my latest work, which is called DOTS. DOTS is an inclusive interface of future spatial computing. So before talking about the design and the products, I really want to share why this process has begun and why we want to do this in the first place. So we are a team from Royal College of Art and Imperial College London, and we're a team of designers, engineers. And about 1 year ago, we met Alec Lutz, who is a thought leader in the disabled community in the UK. So while working with him, we realized that although we were aiming at accessibility of physical things, we gradually realized the digital world could be even more unfriendly to them. So you can probably imagine an amputee use prosthetics to grab a mug. But what about smartphones, remote control, and those small touch buttons on coffee machine? Because of the nature of being designers and engineers, we are facing at this kind of global problems, and we really want to get this done and create a better future for everyone. And so we look into this problem. And there are currently 2.6 million people in the UK who have difficulties using their hands. And there are another 1 million people who have progressive conditions which affect their ability to use their hands. And there's another 41% of disabled people actually have very low access of use internet compared to 75% of non-disabled people. And this is a very big problem. However, it's probably getting even worse. So if you're looking at the trend of digital interfacing, as we can see, the dimension of interface keep increasing. With the dimension, it actually leads to a more complex interface and eventually leads to lower accessibility. So if you're looking at all the big companies, like the trends of future interfacing, it's all about hand gestures, like Google, Microsoft, lip motions. It's all about hand gestures. But what about people without hands? So we ask ourselves how we can change these problems, and we really want to dig really deep to understand what's the fundamental issue behind all of that. And we believe it's actually part of the fundamental reason is the trend of machine learning. So you see all the hand gesture algorithms need a huge amount of data sets to understand what ordinary people's doing. However, every disabled people have different disabilities in different ways, so which is not really reflected with machine learning. So it's very hard to design algorithm that can learn from these disabled peoples. So we ask two questions. First of all, how can we make future spatial interaction inclusive and fits different body conditions? And secondly, if it's not hand gesture, what should it be? So through 6 months of developing and testing, we're so excited to introduce you guys our solution, DOTS, which is what's first customizable interaction system for future spatial computing.
My name is Alex Lewis. I am a 39-year-old I like to go hand cycling, and I also do some skateboarding with my little boy.
My name's Neil Palmer. I'm 42 years old. Getting onto the beaches in the middle of nowhere, that's what I would like to be able to do.
I think we have to remember that for millions of disabled people, we all have very different needs and different abilities. But what I see is all this incredible technology being aimed at an able-bodied person. And what I'd like to see is the technology being looked at to accommodate people with disabilities like mine. Way of looking at working. I think because of that, you've made it, we're all on the same page, which is amazing.
Right, so this is the video of the design, and if it's kind of laggy, I can definitely share you guys the link afterwards. So now, how do we get there? So in the very beginning, we made a very strong assumption that there must be underlying logic of how people use their body gesture to express themselves. So in order to find the pattern, we set up a series of experiments. So the participants will randomly get body parts, two body parts that they can use to express the intention of the four fundamental units in 3D computing, which is selection, moving, rotating, and scaling. So we found like 20 people, and we gathered them into our lab, and they will be like randomly choose two body parts. So somebody like get cheek and mouth, some others get like arm or leg, things like that. And we asked them to do that four movements. And they are actually four fundamental units in 3D computing. And we realized that all that four fundamental units can be expressed with two relative motions of two body parts on your body. So how do we find that? So we record all those people doing the similar movements. So they are signed with different body parts. But when they trying to express, let's say selecting, there are actually very clear pattern that they're trying to move 2 points on their body together. And if you look at movings, there are actually similar patterns. Scaling and rotating, all following very similar patterns that they're trying to use 2 points of their body and use that relative motion between that 2 points to express their intentions. So we get our insights is that we should use the combination of different body parts to control complex systems. And we can really learn people's intention by just tracking 2 points on their body of their relative motions. So that's what inspires to design DOTS. So we designed DOTS, which was first customizable interface for future spatial computing. And it's actually quite simple, it's just 2 points with 2 stickers. And the patients or the disabled people can just put anywhere on their body that they feel comfortable to move around. and just have two dots and one charging base. And what inside of those is very simple. It's just two IMU sensor, Bluetooth module, and one battery. That's how simple that is. So that's what we use to actually measure the relative motions on the body, and those data will come through stream to our computer or whatever they want to control, like AR glasses or VR, things like that. And we will have an API to actually translate those data into the hardware's interface. Right, so that's like the detailed engineering aspect of the DOS. So this is the overall design, and we actually formed a startup just called DOS, and we really want to make this thing come true. So now I want to go through the roadmap of DOS and how we want to change mixed reality industry with our design. So at phase one, next 2 to 3 years, we actually want to just empower disabled people to use smartphones and PCs with our solutions. And after that, we will think about improved lab quality and work efficiency of both disability people or industry users with AR and IoT. And in the far future, we actually really want to set a new standard of embodied instruction for future spatial computing. So in the near future, we really want to actually help everyone to control their smartphones or PCs so that we can improve their level of independence, quality of life, and reduce the cost of social care. So this is actually a trial we did to use DOS to control PCs. So we already conduct a series of user trials that they can actually just use arms or legs or facial recognitions to just control laptops. And this scenario too is like we envision in the future that we can just use gestures to control not only smartphones, laptops, or AR glasses, but also everything you're looking at. So that will lead to a future that we're going to connect AR glasses to all the IoTs around you. And we believe that it will be dramatically increase the living quality of disabled people. Right, so this is overall what the DOS is all about. And I want to end this presentation with a quote from Alec Lewis. After using our product, he says, "This is a new way of looking at the world, and we are on the same page now." So that's exactly what we want to achieve with our design. So thank you very much. And I'm Valentin, so please feel free to contact me, and I have my URL and email address here. So very glad to be here to talk about my design with you guys, and let's open up a more inclusive future together. Thanks.
Hey, thank you very much, Valentin. That was really interesting. As I said, if you have any questions that occur to you from Valentin's presentation, then please put them into the Q&A section, and we'll take all questions at the end of the webinar. Right, well, thank you for your presentation. So now I'd like to hand over to Chiara for her presentation. So Chiara, if you please. Let's see.
Good morning. Can you hear me?
Yes.
Okay, I'm Chiara Walzolger, and I am a PhD student in cognitive science, both at the University of Trento and Lyon. And my research projects explore the cognitive mechanisms involved in spatial hearing. Today, I will present the VR approach I'm using in my research to test and train the ability to localize sounds. In particular, I will present the results of an ongoing project involving people with bilateral cochlear implants. Hearing impairments are a challenge from an economic, social, and health point of view. As reported by the World Health Organization, this problem with different levels of severity can involve elderly population, adults, and even younger people. In recent decades, available technological tools for the recovery of acoustic information have continuously been developing. And more people are using hearing aids, and more recently, the practice includes surgery for the application of cochlear implant, a neuroprosthesis that is able to partially restore hearing experience. So far, researchers have mainly tried to make these devices more effective in capturing linguistic information. However, the hearing experience is still challenging for these people. For example, listening a noisy context, like the one that you can see in this picture, and directing attention towards the person who is speaking is really difficult for hearing impaired people. Moreover, a little explored area concerns the acoustic spatial aspect. The information provided by the system or systems is not sufficient to effectively map the sound space. Localizing sounds for people wearing these devices is not easy. Despite hearing people can put in place tactics to facilitate communication with the hearing impaired people, such as, for example, providing information about where and when to listen or helping with reading. Nowadays, there are still few protocols to help them to improve their own abilities. And most of them are dedicated to understand language. Yet, none trains their ability to identify where sounds come from. Although this ability is fundamental to orient in the environment or identify quickly a potential danger. My research during the PhD has been dedicated to measure and train participant abilities to localize sound. Sound localization is the ability to determine the location of sound sources. When a sound appears in space, it reaches our ear generating binaural and monaural cues. And these cues are weighted and combined to obtain a perceived position in the space, defining horizontal elevation and depth dimension. Our brain is able to create precise correspondences between auditory cues and space. And the result of this process is the creation of acoustic maps of the space. The depleted peripheral input and the variability in the development of binaural skills determine an impoverishment of the ability to localize sounds. And this is the case of bilateral cochlear implant users. To measure sound localization performance, I took advantage of Sphere, our VR approach. This system combines virtual reality with the real sounds in the environment, and allows us to present real sounds from predetermined position, and the experimenter can place sounds around the listener. It allows us also to record the listener's response, asking them to reach the perceived position of the sound. As you can observe in this video, it is possible to see the answers, the green points, and the target source position, the red bars, in a 3D maps. The system gave me the possibility to measure sound localization errors. As you can observe in the data from our lab in this slide, bilateral cochlear implant listeners in green the performance is not comparable to the performance of people with normal hearing in gray, in both azimuth and elevation dimension. In addition to measuring participant abilities, we can also train them. In particular, in the studies I have conducted so far, I have observed the benefit of a reaching to sound training paradigm in which participants localize sounds, choosing from 13 visible speakers. The training was based on active exploration. When I tested participants, I let them the possibility to move the head during the sound, and this stratagem gave me the possibility to propose a natural and ecological situation and to measure their spontaneous behavior. The training was based on visual feedback. During the training paradigm, I informed participants about the correct position of the sounds when their response was wrong by providing a visual feedback. And it was based on motor interaction with sound. In the training, participants were invited to reach the sound source and touch the speaker to stop the sound. This active interaction makes the task super engaging and fosters the potential of the multisensory experience. Here, the video of the experimenter during this training, and as you can see, it is easy to place the sound around the participant and they can move to stop it by reaching the source. In the next video, you can observe what happened from the participants' point of view. They moved the controller in their hand to reach the speaker, and if the answer was wrong, they received a visual feedback. Analyzing participant performance during the training phase, we found that bilateral cochlear implant users can rapidly benefit from the reaching to sound training, as revealed by the fact that errors decrease as a function of trial repetition. To further analyze training efficacy, we tested participants in a different sound localization task proposed before and after the training phase. Differently from the training task, here participants were required to point the head towards sound's direction and not performing a reaching to sound movement with the hand. We found that the training benefit generalized to head pointing sound localization task as compared to a control training situation. Interestingly, most of participants improved. To sum up, I try to extract some tips which may be useful in the clinical practice. First of all, in my studies, I demonstrated that training spatial hearing in cochlear implant user is possible. Furthermore, I observed that permitting spontaneous head movement favored sound localization performance. And this aspect is important, especially when we want to measure participant abilities. Creating ecological setting means measuring more truthful abilities. Proposing ecological setting means also taking into account that sound localization naturally happens in a multisensory context. So vision and other senses can be exploited to solve the task. Furthermore, I have observed that encouraging an active exploration of the acoustic space using head movements and reaching action is crucial to improving sound localization. Even if these observations relate to a very specific sector, I hope that the here outlined tips may also be interesting in other fields of rehabilitation. Thank you for your attention and for this opportunity.
Right, thank you, Chiara. Once again, very interesting. And I look forward to seeing what happens with your research in the future and future applications of that. So thank you. Now let's move on to our last speaker, which is Paul. Paul, are you with us?
Yes, I'm here. Thank you.
Right.
I will share my screen.
Yes.
Okay. Is it working? Almost, yes. Okay. So my name is Paul de Nooy, and I work as an innovation specialist at Bartimeus. Bartimeus is a nationwide center of expertise that provides care to visual impaired people. And in my work, I develop innovative solutions for problems experienced by visually impaired persons. And today I'm going to talk about some of the biggest problems that group experience, and that is finding their way in a building or navigating. So, and my title of my talk is The Future of Wayfinding Aids for Visually Impaired Persons. You can imagine that it is very difficult if you are blind or partially sighted to find your way in a building. We are looking for new technologies that can solve that problem and can help people in finding their way independent. I will show you an example of new technology that is based on computer vision and augmented reality that can assist people that are blind or partially sighted in finding their way. And first, I want to tell you more about what I think is the perfect wayfinding aid. So what it has to do, it has to give you the right information on the right spot, on the right moment, with the right feedback and the right interaction. So yeah, it's complex to do it, and it's of course a lot to do right. And you have to keep in mind that someone has his own navigation skills. So the challenge is to develop an ideal mix between someone's position, orientation, context, and navigation skills. So one of the main parts of a navigation aid, of wayfinding aids, is of course getting the right localization and position of the user inside a building. So there are a couple of localization and tracking technologies on the market that you can use for that. The first is a familiar one, that's Global Positioning Service. It's using satellites, and it gives a position of an accuracy of 5 to 10 meters. But the downside is that it's not working inside buildings, so it's not usable for a lot of people, or it's not usable for a smartphone. The next one is markers or signs. Of course, a marker you can place on a door, and it's recognized by your smartphone camera. It is also a way to localize someone in a building. Bluetooth beacons is another technology. It uses Bluetooth beacons are small devices that send out a Bluetooth signal. And if you place it at the entrance of a building and your phone is near that entrance, near that Bluetooth beacon, it can know its position and can tell the user they are near the entrance. The same is with Wi-Fi. It works the same. It's also a radio signal. Can be picked up by the smartphone. And the last one, I think it's more the future of wayfinding systems. It's working with computer vision combined with artificial intelligence and augmented reality. And I will give you an example of that later on. Computer vision is more like a group of technologies that using the camera and other sensors in the smartphone combined with artificial intelligence to look around and to understand its surroundings, and give the user that information that he needs to find his way. So the future will be more from positioning to more orientation, and the main thing that will increase is that the context of the user is more, the solution knows the context of the user. So the computer or the aid, wayfinding aid, can tell the user what is around him and what he can do with objects, or how to avoid certain places, etc. So it's become a lot more smarter, from static to interactive, from only where am I to what can I do here. So that will be more about the future of wayfinding. We are busy with developing a solution. It's called Augmented Reality Navigation. And yeah, it works as follows. So first you have to scan a 3D map of the building. You have to fill that map with useful information online on a portal with point of interests. And maybe you can add other interesting information like walkable surfaces or other points. It has localization and tracking built in on the smartphone with the camera and the sensors. And the user can follow the route with visual, audible, and tactile feedback. So I will, for all the components, I will give you a more example. So in my presentation, there's a photo with the scanner on it. So it's a 3D scanner. It's also with depth information. And on the right side, you can see the 3D scan. So that's the first thing you have to do. And then you're going to fill that map, 3D map, with information. And I will play a little clip to show you how that is possible. It's like yeah, first person view of the 3D scan, and you can choose for add POI, and then you place it where you want, and you can give it a name. In this case, it's the front desk of a building of Bartimaeus. And so I will also, you see in the video that I place a marker or a POE at a coffee machine. So those point of interest will become destinations in the app, in the navigation app. And I will show you a short clip of it, of the app. There's a screen capture inside the video. But first you have to localize yourself in the 3D scan or in the building. So the application, the system knows where you are. And from that on, you can choose a destination and get feedback how to follow the route. So
tracking successfully
tracking
initialized.
is successfully initialized. So the system knows, yeah, very accurate where you are in that building. And the person in the video is selecting a destination. And immediately the route is visually on the screen with a path of yellow balls. And he hears a sound that he is heading the right direction, and also gets tactile feedback he is heading the right direction. So he can follow the route now. Sometimes he walks very fast because I speed up some of the footage. So you see also other point of interest visually in the video. So that is, I think, the future of wayfinding. And yeah, we are very motivated to work on solutions to give people with a visual impairment the possibility to find their way in buildings by themselves. So thank you for your attention.
All right. Thank you. Thank you, Carl. Very interesting. I remember seeing that an earlier version of that solution.
Yeah,
My research, and was very intrigued by it immediately. So it's interesting to see that it's developed even further.
Yes,
things are happening with it. Right. So those were our presentations. So thank you once again to Paul, Chiara, and Martin for that. And if we can sort of move into the sort of discussion section of the webinar. I mean, one thing that I've noted about all of you is that you're all sort of early career researchers, and you're sort of at the and you're working on these emerging technologies, and that's sort of an interesting, probably gives me an interesting perspective on it. But I sort of wanted to ask, what would you say are the benefits of working with emerging technologies, and especially these extended reality technologies that you're all working with in one way or another?
Right, I can start with my answer. Right, so I think working in the mixed reality especially is definitely fascinating, because if you look at the trend of digital interactions and interfacing, even the internet, mixed reality could really be the new form of internet in the next 10 to 20 years. And as designers or technologists, we really want to sort of study beforehand, so we can actually avoid a lot of trade-offs or problems, and that we can foresee and we can provide solutions beforehand. So when we get to that point, that transaction point, we are really getting ready, and we really actually making a better world for everyone. And I think that's the really point of why designers and engineers want to sort of working at those cutting edge technologies. And for me, it's really fascinating. Thanks.
Yeah, Chiara,
great answer.
Maybe I can add my point of view.
Yeah.
So yeah, I'm a cognitive science researcher. So the advantage of virtual reality basically for me is related to the fact that I can control the visual and the acoustic stimuli I use, and that my participants can experience. So I can also measure head movement or eyes movement in a super controlled manner. So this is the, let's say, bigger advantage that can I have using virtual reality from a researcher, let's say, point of view.
Very good.
Yes, yeah, I'm not really a researcher, but for us, augmented reality or mixed reality, extra reality is very interesting, because it's sort of an interface for the world. We use it, and yeah, we can make that interface accessible for blind and visually impaired persons by audio and also tactile feedback. So that's making, yeah, that's an interesting perspective. And also, yeah, you can use the physical world as an interface. So before internet, when internet was around, it became more visual and also not very accessible for visual impaired persons. So I hope we can avoid that problem again with extra reality, that we can make it accessible from the beginning for our target group. So I think our app is doing that.
Yeah, and your app is still in the demo stages, is that right? Oh.
Correct. Yeah, we are still developing. The video I show was a proof of concept application. So yeah, the idea is that we want to show a prototype version in the end of this year, and then we hopefully can, people can download it in 2022.
Yeah, it's coming up there. Right, we have a question about how we see, how do you see the technology mentioned here? How can we use it to help people on the neurodiverse spectrum, such as ADHD and autism spectrum disorder? I'm not sure if you've looked at that, any of you looked at more cognitive issues. I can say that in my research, I've seen a lot of solutions that deal with that. One big thing that researchers and practitioners are using extended reality and similar emerging technologies for is for simulation exercises and for training. So you can sort of use virtual reality either to experience what it's like to experience your environment as a person with an autism spectrum diagnosis. But you can also use virtual reality to help persons with, for instance, social anxiety or with social limitations to sort of train in settings that might be challenging to them in a sort of safe environment. So those are just two possible applications of these technologies for that specific user group. I'm not sure if you've come across the sort of the cognitive area in your work. I mean, I suppose you, Chiara, because you...
Actually, this is out of my research field, but what I can say is that, yeah, basically you can use virtual reality to simulate what happened in the real world. So you can create, let's say, control situations. So also these people can try to interact with other people, but in a more controlled manner. So I know that also for kind of anxiety problem or something like that, there are some protocols in virtual reality, but this is something that is not really related with my field, so I don't want to say something wrong.
Sure. Another question that's come up is, what are your thoughts on using AI, that is artificial intelligence, in assistive technology in regards to the new EU proposal from April aiming for developing trustworthy human-centered AI? Have you worked with AI in research?
Right, so I can probably give a little bit insight on that. So with DOS, is actually in the project of DOS, the algorithm behind DOS is actually a collaboration algorithm, which the system will actually can't recognize what the maximum moving range of that person. So we can customize the sensibility of the system based on the maximum moving range of that people. So behind that algorithm is actually a lot of machine learning is going on. I think machine learning as an algorithms really have this pros and cons. So as I talked about in my presentation, it's actually a fundamental reason of why mixed reality is getting less accessible is actually because of the machine learning. It's hard to actually get enough data set for disabled people because they are all different. But on the other hand, if a algorithm can actually adapt to different body conditions and to sort of compromise to different body needs, it actually will be absolutely amazing, because if you're looking at certain type of machine learning algorithm like reinforcement learning, it actually helps you to like keep learning on what's going on that people, so we can get a better result on these people. So I believe for the field of accessibility is really about how can we create an algorithm that's not just consider the most, but trying to customize and adapt to different people with the different needs. That will be, I think, the most important thing.
Okay. And are we far away from that, do you think, or?
So from what we see on the industry at this moment, I think there's still a gap there because, well, as a company, you have to make profits. And if you want to make profits, you want to go to mass production, which is you want to fit needs for the most. However, we do see hopes in a lot of fields. For example, I think I see one latest research done by Facebook, Reality Labs, and they're actually sensing the muscle electrics on people so they can understand the micro gestures that are done by certain people. So from my understanding, if you're not using camera to capture the body movements, you actually have a better opportunity to sense different body with different body conditions because you're not using a general analyzed model for everyone. So as long as we can do that, with the uses of reinforcement learning, we can definitely create a more customizable interface. And I think that's definitely a way to go. So there's still a lot of hopes there.
Yeah. Research is needed, perhaps. Yeah. Something that I wanted to ask about is that you, each of you have done use testing in your research and in your work, sort of a big part of the development processes. How has that impacted the development of your research and of your solutions? Did it change from what you thought it would be following the user testing?
I can take this one. So with thoughts, we actually go through I think at least 4 rounds of user testings. So what we do is actually we work with a disabled community. It's actually an NGO based in the UK called Alex Trust. So through those pilot testings, we actually learn really a lot of things from those people. So one very important insight, I guess, is actually very different. Every disabled people have their unique way of understanding things. So imagine we all born with different body conditions. The world will be very different because every people see the world in very different ways. So that's exactly what we learned through the user testing with disabled people because they have very different body conditions, so they do things very differently. So if we want to design something that universally usable for disabled people, let's say, we have to actually expose ourselves in as much as different conditions as we can. So through this user testing, we actually learned a lot, how big that dots should be, what kind of user pattern we should use, what kind of sensing technology or algorithms we want to testing with, what should the calibration process should be. So there's really a lot of things we learned through that process, and I think it's absolutely important. It's probably more important for designers working in disabilities compared to just consumer products.
Yeah.
So yes, that's definitely important.
Yeah. Chiara and Paul, have you had the same experience with user testing and just user involvement in research? Or
yeah, actually, I'm using VR technologies as a, let's say, user because I'm collaborating with the engineer, so I am a psychologist, and sometimes the fact that we think that we have a technology that we can use to do research, in my case, it's sometimes it's hard to understand really well the effectiveness of the technology without testing them. So sometimes we create an experiment with test participants, and then we realize that maybe we need to change something in the technology. So probably it's from my perspective, so a more, let's say, research use of VR sometimes is better to, for sure, is super important to piloting technology before use them, both for research and for other use, let's say.
Yeah.
Yeah, for it's really crucial to do user testing for us, because we have to find out which feedback mechanisms works well in which combination for which users. So there are a lot of different users, blind, partially sighted, walking with a dog, walking with a stick. So they have all their own navigation skills. So that's a very interesting mix between all sort of people. And we have to mix with tactile, audio, and visual feedback. So yeah, you have to do a lot of user testing, what works well and what does not working well. So one of the things we found out was that we have a visual line, and for a blind user, it's also a very narrow line they have to walk on to get the tactile feedback. And users with a dog, they have a lot of problems to follow that narrow line, because the dog is also some thing that helps you walking through that hallway. So the dog has no feedback from the app, so they are not working well together. So that's one of the things we find out with user testing, that it's not working for someone with a guide dog. So
yeah. It's very interesting. So sort of surprise that you can only sort of find when you actually test.
That's just, it's not, it's really something you don't think about when you're designing that sort of thing. So yeah.
No, it's the whole point of it, I guess. A more general question, do you see any potential problems with emerging tech and accessibility, in terms of accessibility in emerging tech?
Yes, the accessibility by design. So it has to be built in from the beginning. So a lot of emerging technologies are not designed with accessibility in mind. So yeah, we have to fight for that. So all the startups and all the cool new companies, we have to make sure they are already including accessibility, so you can read your smart the English word, your smart washing machine or your smart oven. You can, if you are blind, you want to how do you say it in English? You want to get it done. You want to do that. You can have an interface. You can operate. So it's very important.
People haven't really thought about that, or in the design at the beginning. Yeah, is that your experience as well, Chiara?
Maybe I can say just hearing aids or cochlear implants can be considered technology for sure, and they are fundamental for hearing loss. But as I said in my presentation, sometimes we try to help them to understand language, but we forget something about the acoustic space, for instance. So we need also to create technologies that can really help considering all the different details or different levels of perception in this case. So for sure, technologies are fundamental, but sometimes we need to balance very well all the benefits.
Right. should also answer this question. I think it's very interesting question. So I want to get my opinions. So I think in terms of technology, it's like the cons we get from the text. It's actually a really long topic. It's really part of the human history, really. Because if you look at all the technology when they are invented, even like those very old techniques, like for example, like printing, probably in fields like 1,000 years ago, it's still kind of a technology. But every technology, when they created, it leads to new problems. Like if you invented printing, it will lead to less accessibility for those people cannot see. So I think a very nice thing is at least now designers and design for accessibility is part of the conversation, is on the table. So as long as we are part of the conversation, we can make impacts. So I think I have like a very positive mind on the future of design for accessibility because it's already a part of the conversation. So we definitely can make more things that works for everyone.
Yeah, that's very interesting. In this context, I just wanted to mention something that our friend Josh O'Connor from W3C pointed out in the chat, that they're actually working on identifying user needs in terms of extended reality, in particular at the moment. And they're inviting people to help them that work. So I'm going to share the link to those XR accessibility user needs for people to have a look at. There's some very interesting work happening in that space at the moment. So yeah, when I think we've neared the end of our webinar. We had one final question from Valentin, just about the requirements of websites and apps using dots. Do you meet the WCAG criteria, or have you looked at that? Or
sorry, actually, I tried to find that question, but I cannot find in my interface. So could you repeat that for me, please?
So the question is, what are the requirements for websites and apps to be able to access them using dots? Are the criteria WCAG 2.0?
Right. So we're still actually using APIs. So we're building our own APIs. So we're actually building some APIs for some very popular hardwares, for example, like HoloLens. So at this moment, if one hardware want to use those, we have to sort of customize a API for them. So we're currently working with, so like we build some API for HoloLens for like some smart lighting company like Philips, that they have a smart lighting called Hue. We built a API for that as well. And we're also working on something that can be used on iPhone. So that's like, at this moment, we still need to adapt one by one.
Okay, brilliant. Right, so I think that does it for our webinar. So thank you once again to our panelists, to Valentin Weinongong, to Chiara Balsolger, and Paul Denoy for joining us here today and for your very interesting presentations. Thank you all for your attendees for your questions. And if there are some questions that you didn't feel we got answered, then please reach out to us and we'll try to help you with that. As we said, the recording of this webinar will be available on Funka's YouTube channel. So if you want, please have a look there. Right. Well, thank you so much, everyone. And yeah, until next time.
Thank you.
Yeah.
Have a nice day.
Thank you.
Bye.
Thank you. Bye.
Bye.